Hi there, this is the fourth video on functions for AS Mathematics, and in this video we're going to be looking at the inverse function. We've talked about terms and definitions. One of the things that we need to understand in here is what the inverse function is. So we're going to deal with that today. The syllabus specifically says find the inverse of a one-to-one function in simple cases and illustrate in graphical terms the relation between a one-to-one function and its inverse. So we're going to be talking today all about the inverse function. So an inverse function, as the name implies, undoes the effect of a function, and the notation we use is this: f to the minus 1x. Now this notation can be a little bit controversial because we're used to seeing indices like this and thinking when we say something like y to the negative 1 that represents the reciprocal function, and that is true in algebra. But here this is just a notation to tell us that we're talking about the inverse function. There are other notations, but this is the one that we're going to use here. So one of the things I'm going to go through is see how, if you have the domain of a function and the range of a function, then for the inverse function those two are swapped around. So the domain of the original function becomes the range of the inverse function and vice versa. So let's just look at a few examples. If we have a function that's double the number, so 2x, then the inverse function is just half the number. If a function adds 4 to a number, then the inverse function would subtract 4. A more composite example, if we multiply by 3 then subtract 1, and the order is important, then adding 3 and dividing by 3 would undo the effect of that function. And of course, squaring a function, the inverse of that is the square root of that function. So there's some really basic examples of what inverse functions look like. You can define it also just using composite functions. If we apply the function of the inverse, then we're just going to get back to the original number, or the other way around. If we do the function first and then apply the inverse, we're going to get back to the original number. So think of it sort of, if you had a function where you added 4 and then you applied a function that subtracted 4. So whatever number you put into here, you're going to get that number out that you originally got, okay? And it doesn't matter which is the original, which is the inverse, and which order you do it in here. That couldn't be used as a definition of what the inverse function is. So you can see this first example here, it's asking us to show that the inverse function is that. So we need to show either that this is true or this is true to show that those two functions are inverses. So using the same kind of thing we did with the composite function, f of x plus 1 over 3, so f of the inverse function, the function here is 3 times the number minus 1, so 3 times this thing here minus 1. Bit of algebra here shows us that we get back to the original function. So that proves that this is an inverse function, or you could do it the other way around as well. You could start with the function and then apply the inverse function to that to show that we get back to the original value of x. So you can do that with x equals 2 as well and show that putting 2 in you get 2 out, either way around. As I said earlier, the domain and the range kind of swap around, and that's an important one to recognize here. The domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. So you'll get questions like this that say, we've got this function, here's this quadratic function here, defined for x, any real number, find the domain and range of the inverse function. Well, if you can work out the domain and range of the original function and just swap them around, you've got the domain and range of the inverse function there. So, and I think that's what I've done here. Completing the square on this function, we get x minus 2 squared minus 2. So I know that this is a quadratic function with a turning point of 2 minus 2. There it is there. And we know it's going to be concave up like that. And we can work out the y-intercept as well if we wanted to by putting x equals 0 in there. So that gives us 2. So we've got a sketch of the function there. We can see the domain is any x value. And we can see the range of this function here is y values greater than or equal to minus 2. Alright, so minus 2 and above. So if we now just swap those two around for the inverse, the domain of the original is x is any real number. So the range of the inverse is y is any real number. The range of the original function is y greater than or equal to negative 2. So the domain of the inverse function is x greater than or equal to minus 2. Notice how we have to swap around x and y here when we're talking about domain and ranges. Okay, we always talk about the domain, meaning what are the possible x values, and we always talk about the range is what are the possible y values or f of x values. It's really important to understand the relationship between a function and its inverse. In fact, when you look at the two graphs from the previous one, we've got our original function there in red, and then we've drawn that inverse function there. You can see, we've drawn the inverse of that original function there. The relationship is that one graph is just a reflection in the line y equals x. That's all it is. And that makes sense because what we're doing is we're really just swapping the points around. So if 3 minus 1, this point here, is on the original function, remember we just swapped the x and y values. So 3 minus 1 is on the original function, then the point minus 1, 3 is on the inverse. So minus 1 and 3, so that's right there. That is that point there on the inverse function. Okay, and these points are just a reflection in the line y equals x. So if you take this point here and reflect it over in the line y equals x, you get that point there. Okay. If you take this point here, 1, negative 1, and reflect it over in the inverse function, you get negative 1, 1, that one there. So you've got this reflection idea in the line y equals x, or we're just swapping around the x and y coordinates of any point from going from the original to the inverse function. So let's look at a few examples of that. So if we've got f of x is 3x minus 1 and we want to draw the inverse. Well, there's a number of ways of doing this. You can draw y equals 3x minus 1, which is the red line there, a gradient of 3 going through minus 1, and then you can just reflect it in the line y equals x. Now, you're not going to get it very accurate. If you want to get it accurate, you could just do some points. So for example, this graph goes through 0, minus 1, the original function. So that means that this point, minus 1, 0, will be on the original, the inverse function. There it is there. Another point on the original function is 1, 2, so that we know the point 2, 1 will be on the inverse function. So 2, 1, that one there. So you can see those are just reflections in the line y equals x. So you could do that a number of times. In fact, I guess all you need is 2 points. Once you've got these 2 points here, you can just draw a straight line between those 2 points and you've got your inverse function there in blue. So that's one way of doing it. The other way of doing it is you can just do it algebraically as well. So if you can work out that 3x minus 1 is your original function, then this function is a result of multiplying by 3 and subtracting 1. So the inverse function, going in reverse order, will be add 1, divide by 3. So the inverse function will be this line here. So it's x over 3 plus 1/3. So it's a line with a gradient of 1/3 and going through 1/3. So that's another way of drawing the line, but you just really need to know the relationship between a function and its inverse on the Cartesian plane. One of the things you may have noticed in a previous example is when I did the inverse of this function here, the inverse was not a function. That's a really bad drawing of it, but you could see that that black line that I've now drawn is not a function. So in other words, for a particular x value, we have 2 different y values. So that black line there, in fact, is not a function. So another test of one-to-one function is that if we did the inverse, and that also is a function, then that function is 1-to-1. Alright, so this function that we've drawn here, parabola, is not 1-to-1 because the inverse is not a function. So there's another definition. A function is 1-to-1 if its inverse is also a function. So one of the questions that you'll get commonly here is about restricting the domain of the function so that it is 1-to-1. In other words, so that the inverse is a function also. So imagine if we just forgot all of this part here and just started from here onwards, then we would get something, and we were reflecting this in the line y equals x, then we would get something that looked like this, and now this curve here is actually a function. For each x value on this curve, there's only one y value. Okay, so that would actually cross over about here. So this one here I'm not doing very accurately, but you get the idea. If we restrict the domain of the original function, then we can get an inverse that actually is a function, and that function is then 1-to-1. Here's a graph of what that looks like. Okay, so we restricted the domain so that x is greater than or equal to 2. We've split that parabola down the middle, and now the inverse is also a function. and so that original function there is 1 to 1. We could also do it so we take the left hand side of the parabola, so x value is less than or equal to 2. You can see also that the reflection of that red function in the line y equals x is also a function. So if we restrict the domain to x values less than or equal to 2, we get a 1-to-1 function, or the inverse is also a function. As I've noted here, you could just say x value is greater than or equal to 3, and that would also be 1-to-1. But a lot of questions will ask you what's the least value of k that makes the function 1-to-1 for x values greater than or equal to k. What's the least one? So in this case, we want k is equal to 2. X value is greater than or equal to 2. That's the least value that we can use so that the function is 1-to-1. So let's talk about finding the inverse algebraically. Earlier on I said how you can just swap the x and y values over to get the graph of the inverse. So if the point 2 minus 1 is on the original function, then the point minus 1, 2 will be on the inverse. So being able to do that, and that idea of the inverse being a reflection in the line y equals x, suggests a way that we can work out the equation of the inverse algebraically, and that is basically to swap the x and y values in the equation. So that's what I'm going to do. Swap the x and y values in the equation, rearrange it so that y is the subject, and then rewrite it as the inverse function. So if we have 3x minus 1, we want to find the equation of the inverse. Now I did this previously because I just kind of understanding it, but another way of doing it is like this. So if you start with 3x minus 1, that's the original function. The inverse will be this function here. We've just swapped the x and y values. So every time we see y, we put x. Every time we see x, we put y. This is the inverse function right here. And now all I need to do is rearrange this equation by adding 1 to both sides, dividing by 3. That is the inverse function, and then rewriting it with f to the minus 1x is x plus 1 over 3. A lot of these examples you'll see involve quadratic functions. So here's a function, g of x is x squared plus 6x plus 2, x is greater than or equal to k. Find the least value k for which g of x is an inverse. So what we're really asking here is split this quadratic equation down the middle, this quadratic function down the middle, and find what's the value of x that splits it down the middle. Alright, so that the function, the least value of k when x is greater than or equal to a certain value, so that it has an inverse, which means that the function is going to be 1-to-1. Okay, so that the inverse is a function. That's another way it's written in the exam, so that it has an inverse, but that's what it means. So that the inverse is a function. Alright, so if we can complete the square here, we get x plus 3 squared minus 7. So we know this is a quadratic function with a turning point, a vertex at -3, -7. We know it's concave up, so you can see my red diagram over there. I've drawn it. Again, you don't have to have this super accurate, but doing a little sketch really helps. So you can see to split this thing down the middle is going to have to be at -3. So -3 is the value for that first question. We want x greater than or equal to -3. In other words, we're going to take the right hand side of this thing here, and if we were to reflect it in the line y equals x, we would have a function. The inverse would be a function. Alright, so the answer to the first one is k is going to be -3. So it's just what's the value of x that splits that quadratic down the middle. Part B says find the equation of the inverse in this case. Alright, so we're looking at what's the equation of the inverse function. So here's my original function. And as I said, just swap the x and y's over. So wherever you see y, put x. Wherever you see x, put y. So this is the inverse function. But it's not as nice as we want it because we want it with y on its own. So we want this as a function of x. So we need to do just a little bit of algebra. So add 7 to both sides here. Then we take the square root of both sides. Now notice we didn't do plus or minus here, because we're talking about the right hand branch of this thing here. So it's the branch that we're going to get is going to go something like that. So it's going to be the top part of the inverse function. If we wanted to take the values of x less than or equal to -3, then we would be dealing with, let's draw this in a different color, something like that, the bottom part of that function. Alright, so just be aware of which one it is that you're taking. If in this case it was less than or equal to -3 we're looking at, then I would take the negative root here. It would be the -1 that I'd be looking at. But in this case here, it's the positive 1. Okay, after we've got that, I'm just going to subtract 3 from both sides here, and that is the function. That is the inverse function, and just rewrite it as g to the minus 1x, that's the notation, is equal to root x plus 7 minus 3. So that's the equation of this black part here. Alright, this one here just says we'll find the expression for the inverse, so I'm going to do the same thing. Rather than h of x, what I'm going to do is just replace that with y. So call that y equals 3 over x minus 1. So from here to here, all I've done is swap the x and y values. So this is the inverse function. But we want to, of course, write that in terms of x, so we just need to rearrange it. So multiply both sides by y minus 1 gives us this. Then we're going to divide both sides by x. Remember, I'm trying to get y on its own, and then add 1. So that is the inverse function, and we just rewrite it. H to the minus 1x is 3 over x plus 1. And you've got the diagram here. You just won't have to draw these diagrams, but I just wanted to show you the original function there in blue and the inverse function there in red, which is just a reflection in the line y equals x.